Okay, let's go. So, integration by substitution. So this is what we're going to use now is first technique of finding antiderivatives, right? Integration, like I explained yesterday, is finding the antiderivative. This technique would be the equivalent of the chain rule for derivatives. Okay, so to do the derivatives, when you have a function inside a function, you do a chain rule. And when you have a function inside a function and you want to find the antiderivative, you're going to use a what we call a U substitution or substitution. Okay, so let me just start with an example. Okay, and you will see the process. So the integral, so the antiderivative of, let's say, x times the cosine of x squared dx. Okay, so let's say I want to find the antiderivative of x cos of x2. Okay, so if I ask you to do this, I mean, I don't know how you would start. Okay, if you have no clue what to do, okay, unless you know already what to do. Okay, so the thing that I notice is that I have the cosine of x2. So it's a function of a function. Okay, so this is a composition of function. If you were to derive this, if you were to find the derivative of this term here, cos of x2, you would have to do a chain rule, right? It would be negative sine of x2 times 2x. So since there is a chain rule involved when we derive, chances are, it's not sure, but chances are that this, what's inside, is what I'm going to call u. Okay, I'm going to show you what I mean by that. Okay, so I'm going to let u is equal to x2. And so this means if I do the derivative now of u with respect to x, so du dx is equal to what? What's du over dx?
2x.
Very good. 2x. Okay. And if I continue a bit further, I isolate du. So du is equal to 2x dx. Okay. And then if I isolate dx, or, okay, whatever, if I isolate dx, or if I isolate x dx, because I have an x dx here. Okay, you recognize x times dx right here. So let's say that du over 2 is equal to x dx. Do you understand what I just did? Okay, so again, I looked at the function that I want to integrate. And I noticed that there's a term that has a function inside a function. Okay, so this is a hint for me that what's inside here is what I'm going to use as u. Okay, so that's what I'm doing. U equals x2. And then I'm going to just find my relation between my differentials. Okay, so basically du dx is 2x. I just do regular derivative. And then I isolate x dx, which is what I find in my integral. The rest is x dx. Okay, and now I could rewrite this integral only using u's, no more x's. Okay, so I'm going to write equals the integral. So cos of x2, but x2 is u, so this is equal to the cosine of u. Okay, times x dx, but x dx is du over 2. So I'm going to write here times du over 2. And that's a very easy integral. This would be, we should be okay with this. Okay, so I continue here. I'm going to pull out 1/2 times the antiderivative of cos, which is what? What's the antiderivative of cosine?
Minus sign.
No, plus sign. Okay, so be careful. That's a typical mistake. So sine u plus, don't forget, if you derive sine, you get cosine. Good? So that's it. From here to here is the step where I found the antiderivative. The only thing left to do is to re-express everything now in terms of x's. So I replace the u back by x2 and I'm done. Okay, so this is equal to 1/2 times the sine of x2 plus c, and this is my answer. Okay, so if I do the derivative of 1/2 sine x2 plus c, I should get x cos x2.
But sir,
Yeah.
where did the du go?
Where did the what, sorry?
Where did the du go? Like,
From here to here?
yeah.
Here to here?
Mm-hmm. Yes.
So once you find the antiderivative, the s, the symbol, and the du disappear. Okay?
Okay.
It's like applying the antiderivative operation on this function. Take it out, that's it. You apply it. Just like when you do derivative, you put a prime. Once you derive, you don't put a prime anymore.
Okay. And let's say like at the beginning it was cos x power 3, then u would be equal x power 3.
Yeah, exactly. And it doesn't guarantee that it will work.
Okay.
If this was an x3, right?
Mm-hmm.
Good question. If this was x cubed, this would be 3x2,
Mm-hmm.
right? And then I wouldn't be able to isolate x dx anymore. I would have x2 dx, and I'll be stuck. I would be stuck. You're right.
Okay.
I don't know how to do that. Okay, can we continue? We want to try one. Okay, try one. So let's say the integral of okay, do you want to try it on your own?
Yeah.
Okay, try it out. Okay, I'm giving you a few minutes. So I'm going to put u as x4, which means that du dx is 4x cubed. And since I have an x cubed dx here, I will isolate the x cubed dx. And so du over 4 is equal to x cubed dx. Okay, then I replace. Integral becomes so secant squared of u, right, of x4, which is u, times x3 dx, which is du over 4. And that is equal to 1/4 times the antiderivative of secant squared, which we know is tangent. And I replace now the u back by x4 and I'm done. there any questions?
Sir, where did the 1/4 come from?
This quarter here,
Yes.
this one here,
No, the one below.
this one,
Yes.
this
Yes,
one.
this one.
So I just pulled out the quarter outside. Right, 1/4 came outside of the integral.
Okay, and the sec, because the sec is 10, but the sec over 2, it's not 10/2.
Sorry, what did you say?
The sec to the power 2,
Huh?
like normal sec is 10, but
Normal sec is not 10, who said? The antiderivative of secant?
yes.
No. The antiderivative of secant is complicated. I don't know. What should you derive to get secant? I don't know.
Okay, so why did we write 10 then?
Because what's the antiderivative of secant squared? What should you derive to get secant squared?
Oh, okay.
Tangent.
Okay, perfect. Yeah, it's fine. Thank you.
I have a question. Where did the x3 go? X to the power of 3?
Sorry, x to the power of 3.
Yeah.
Where did it go?
Yeah, why didn't we just exclude it in the second one? Like when we rewrite.
Here?
Yeah.
Okay, because here I have x3 times dx. You see it on top here? I'll just highlight it here. So x3 times dx. Okay, this is exactly equal here, x3 times dx is equal to du over 4.
Okay, yeah, thank you.
Replace the x3 dx by du over 4.
Okay, thank
The
you.
whole idea, the whole point is to re-express the integral in terms of u only, no more x's. And hopefully, I hope to get an integral that's much simpler to evaluate, which is, at the end, I end up with the secant squared, and I know that the derivative of tangent is secant squared. Does that answer you?
Yes, thank you.
Okay, any other questions?
I'm still not sure
Yeah.
how du equals 1.
How du equals 1?
Yes.
Where did you see that du equals 1?
Because when you put in the integral, it changes from du over 4 to 1 over 4.
Oh, no. Okay. So this step, okay, let me just do an extra step here, okay? Because you guys are confused here. So I'm gonna erase this 1 second.
Sir, didn't you just factor 1/4 out?
Yeah, that's what I did, but I guess I skipped a step. I'm gonna put it back in. Okay, so this, I'm just pulling out a 1/4 here. It's 1/4 times the integral of secant squared u du. This is what this is. This okay? This equal here? You understand this from here to here?
Yes, sir.
I just pulled out a quarter, and now I just have a very easy integral. The integral of secant squared. I know it's tangent. You get it?
Yes.
That's it. And now I just rewrite the u as x4 and I'm done. That's it.
Always remove the dx at the end, right?
So from here to here,
Yeah.
to here, okay. So I have integral du is like the operator on this function.
Mm-hmm.
So it comes to this function and it transforms it into the antiderivative. Once I found the antiderivative, that's it. I don't need the operator anymore. Okay. But it's like if you write, I don't know, x2 prime, you write this is equal to 2x, right? And you keep the prime. There's no more prime, that's it. You evaluate it, that's it, no more prime.
Okay, yeah.
It's like if you're asking me why isn't the prime there anymore? That's it, because you just found the integral.
Okay.
Right? Here the derivative, here the integral. Okay, good. Ask more questions. If you have, ask questions. Okay, so slowly, slowly we're building. There's no use of going fast. Okay, because this, what we're doing now, we're going to use the whole course. Okay, all the other techniques, you're going to need the substitution. Okay? It's basic. That's why we do it first. So we have to make sure you understand this. No questions? I can erase.
How does sec squared u du become tan u plus c?
The plus c, forget. It's just, right, it's the constant. But how does the second square become tangent?
Yeah.
I'm finding from here to here. So from here to here. I don't think there's space. I'll write it here. So from here to here. Okay, this step, we are finding antiderivative. Finding. Antiderivative.
But what happens to the du?
So it's exactly what I just explained. Okay, so 1 second, I'm just running out of space. Okay, let me just erase this. Take a screenshot if you need.
Okay.
So another example. So integral of, let's see, x times the square root of 3x2 plus 1 dx. Okay, and I'm going to set you up with another one right away. What do we use as a u here?
3x squared plus 1.
Very good. So 3x squared plus 1. And so du dx. So du dx will be, what's the derivative of 3x2 plus 1 is
6x.
6x dx. Is that okay with you?
Yeah.
Okay. So now here I have the x dx. So I'm going to isolate x dx here. So x dx is equal to du over 6. And now I just need to express the whole integral with just u's. I could do that now. So square root of u times, right, x dx, which is du over 6. And this is equal to 1 over 6 integral of, well, square root of u is u power 1/2. Okay, so it's 1 over 6, and the integral of u power 1/2. So this is a power rule, right? U power anything. So it's u to the power of So a half plus 1 is 3 over 2 over n plus 1, which is 3 over 2. Is that okay? And so the answer will be, so 6 times 3 over 2 is 9, so 1 over 9 times u power 3 over 2, so basically u, which is 3x2 plus 1 power 3 over 2 plus, there you go. This is the antiderivative of that. Okay, if you do the derivative of this expression, you should get x root of 3x2 plus 1.
Sir, I'm not sure I get the last part.
Sorry.
The last part, like where you did u power 3 over 2, I don't get that.
This part here.
Yeah.
Okay, so this part is okay. This here is okay.
Yeah.
Okay, so I just want this part. So this, so from here to here, this comes from the integral of u power n du is equal to u to the power of n plus 1 over n plus 1. This is the power rule.
Oh, okay, okay. Yeah.
Okay, remember? So n is 1/2, which you get.
Okay.
So I'm just always wondering, where does the x go? Like the x before the function?
X before the function, this one here,
Yeah, it always disappears, but I don't know. Okay.
because x dx, right? It doesn't disappear. I'm just replacing x dx by du over 6. I mean, x dx here, you see it's equal to du over 6.
Oh, okay, yeah, right.
Dx by du over 6.
Yeah, okay, yeah.
Okay.
Yes, thank you.
It's all a question of substitution. That's why it's called integration by substitution. Okay. Next one.
So wait, I have a question.
Yeah.
How did you get to the 3 over 2?
This 2 over 2 here.
Yeah.
It's because I want to integrate u power 1/2. So u power n is always u power n plus 1 over n plus 1. So if this is a half, this will be a half plus 1 is 3 over 2. A half plus 1 is 3 over 2. No?
I mean, I guess I'll get it later.
No. You're not gonna get it later, you have to get it now.
So wait, this is just the formula itself?
This is the power rule that we did yesterday.
Okay.
Okay. The power rule tells you that the integral of u power any exponent, of course, that's not minus 1. Okay. Because if it's minus 1, it's 1 over u and that becomes 1. But let's say n is not minus 1, which like here it's a half. So u power a half, if you want to integrate this, you get u power a half plus 1 over a half plus 1.
Okay, I get it.
No, you don't get it. You sure you get it?
Yeah, I actually understand. I didn't get what the n was until like you said.
N is the exponent.
Yeah, okay.
Power. Okay, this one here, the second one, what did you use as u?
The denominator.
Very nice. Okay. Okay, so the denominator. So u is 1 minus e to the x, and so the derivative. So du will be negative e to the x dx. Is that okay? Okay, so du over dx is negative e to the x, and I isolate du. Okay.
Sir,
Yeah.
why do we use u as the denominator?
Because if you think about it, it is a function of a function. So 1 minus e to the x is a function. What did I do to that? I put 1 over that. So it's 1 over that function. So I did two things on the x. I did a few things. I did 1 minus e power x. And then once I have this function, I put 1 over that. Okay? If you were to derive 1 over 1 minus e to the x, you would have to do a chain. No? I don't know who asked this question.
Oh, it's me. And should we not use the quotient rule
No.
if you want to?
There's no quotient rule in integral. I'm not finding the derivative here, I'm finding the antiderivative. If I'm asking you to find the derivative of this, true, you have to do the quotient rule, you're right. But that's really not our problem now. I'm going backwards. What should I derive to get this? You understand this?
Yeah, a little bit.
A little bit means no. Okay? So it's either you really understand it or you don't understand it at all. So let's go again. Okay, slowly, take our time. This is new for you. So there's no reason to be ashamed to ask questions. It's normal that you don't get it right away. Okay? So again, how do I decide what I'm going to set up as you? So remember, I'm trying to find the antiderivative. If you're telling me, if you're asking me, why don't we use the quotient rule here? It means that you're still blocked in your head in finding derivatives. We're not finding derivatives. I'm not interested in that now. I'm asking what function did I derive to get this? That's what I'm asking. Okay, it's much more complicated. Okay, so to do so, okay, I could do guess and check, guess, try until I found a good one. And it's going to take me time. Or there's a trick that works in this case. Is that 1 second? I noticed that if I do the derivative of the bottom, I get something that's very close to the top. Right? If I do the derivative of 1 minus e to the x, I get minus e to the x, which is almost e to the x. So that's a good indication that I should use this as a same as here, if I do the derivative of 3x2 plus 1, I get something very close to x, right? I get 6x. So if you see that there's a piece that when you derive, you get the other thing that's outside on its own, chances are that's what you're going to put as a u. Okay, so here you notice 3x2 plus 1 derivative is 6x, very close to x. 1 minus e to the x you derive, you get minus e to the x, very close to e to the x. Okay, of course, if on top, instead of having e to the x, I had just an x, then we'd be in serious trouble. Okay, you have no clue what to do. Okay, but I posted the question, right, in a way that's doable. I put the e to the x here that's waiting for the derivative of the bottom. Do you understand what I'm saying? Or I just stop?
Yeah. And I still have a question. With this particular example, is there a function in another function?
Yes, there is. Okay, because it's a compositional function here. It's like I'm going to write it fits here. So let's say f of x is 1 minus e to the x. Okay, and here we have 1 over f of x. See, it's 1 over a function. It's a function of a function.
Oh, okay.
Okay, so it's a composition. It's like g of x is 1 over x, and it's g of f of x. Okay.
But sorry?
Yeah.
Like if we just had like 1 over e power x, like just that, then we wouldn't have to do all of this?
If you had 1 over, sorry?
1 over e power of x, like if there was an x on the top and bottom?
If there wasn't,
Like,
if it was what, sorry?
Is the reason why we have to do this because there's an x on the denominator and the denominator?
Just an x or an e to the x?
Well, e to the x in this case.
In this case, yeah, because there's an e to the x here as well, yeah. If on top it was cos x, you're stuck.
Okay.
Okay. Okay, so let's continue. So e to the x dx is therefore e to the x dx is negative du. So now let's replace everything. So the integral of, so 1 over, so 1 minus e to the x is u, so 1 over u times e to the x dx is negative du. And that's a very easy integral, again, okay? So this, the whole point of the substitution is to end up with a very easy integrals, and that's an easy one. Okay, so negative integral 1 over u du, and this is what? Negative log absolute value of u plus c. And if I replace the u back by this, I'm done. And this is my answer. Okay, 2 examples. What did you use as a u here?
Squared minus x.
Sorry?
X squared minus x.
X squared minus x, because I noticed that if I do the derivative of x squared minus x, I get 2x minus 1. Okay, that's what goes on in my head. Okay, so u is equal to x squared minus x. Therefore, the derivative, so du, derivative of x squared minus x is 2x minus 1 times x. So I just replace everything directly in the integral. And so this is the cubic root of u times 2x minus 1 dx. It's just du. And this is basically u power 1/3. And I use the power rule. So it's u to the power of 1/3 plus 1 is 4/3 over 4/3 plus c. Okay, and so this is equal to, I'm going to replace the u back by x2 minus x, right? And so divided by 4/3 means 3/4. times u, which is x squared minus x power 4/3 plus c, and this is my answer. Okay, questions? That wasn't so difficult.
Sir, could you repeat the last step again?
This one here?
Yeah, how you got that from the other one.
Okay, so it's if I divide by 4/3, it's like multiplying by 3/4. That's okay.
Yeah.
Okay. And then the only thing I did is I replaced the u. The u I replaced by x2 minus x.
Okay, okay.
That's it.
So you just replace the u back.
Yeah, this is u power 4/3.
Yeah, sir, the 3/4.
Yeah,
Where did you get it from?
if you divide by 4/3,
So we just multiply by 3/4.
or by 3/4.
And why didn't we divide like the du divided 2 in the first place?
Sorry.
With the pink. In the pink?
Okay, what about it?
Why didn't we divided the du by 2?
Why do you want to divide by 2?
I did the same thing, sir. I factored out the 2 from the equation.
Yeah, me too.
You factor 2 here,
Yeah,
x minus a half,
yeah,
and then you put a 2 on the bottom here.
yeah.
Why would you do that?
To just to take out the 2, like the coefficient.
Why does the 2 bother you?
Because usually in the other equation we used to divide by the number which is
No, what I did is I want to make sure that what I have here is exactly what I have here. That's what I want. See, 2x minus 1 dx, 2x minus 1 dx. So that I could go back here and replace this by the.
yeah, okay, right.
That's it. I already have it. I have 2x minus 1 times dx. That's it. I stop. I have the right away. Why do I want to complicate? If this was, for example, 4x minus 2, then right, I would have to multiply this by 2 and this by 2. I have to make sure that what I have here is exactly the 2x minus 1 x. I've seen it.
Okay, thank you.
I have a question. Why didn't we use a 2x minus 1 as the value of u?
Why did we? I'm sorry.
Why didn't we use 2x minus 1 as the value of u?
You could have, but it won't work. If you put.
That's what I did.
Okay, well, it doesn't work because if you do the derivative of 2x minus 1, you just get 2.
Yeah.
Right? And that's not what's left.
Okay.
You have to make sure that when you derive, that's one reason. What you derive gives you whatever's left outside of that. Okay? That's one reason. The other reason is that 2x minus 1 is not a composite function. It's not a function of a function. There's no, if you were to derive this, there's no change. Understand? The derivative of 2x minus 1 is just 2. It's just 2.
Yeah.
But if you want to derive this expression, which is x2 minus x cube root, so there's a function of a function. The function x2 minus x to which you're doing a cubic root. There's two things happening here. So since when you would derive this, you would do chain rule, chances are the interior part is what you're going to use it.
Okay.
Okay? It's normal that you don't see it yet because you just started with this, but you'll see. You'll do maybe 10, and it's gonna become more natural. You see right away you say, oh, this is what I'm going to choose as. Of course, if the substitution works. If sometimes it doesn't, you have to do other techniques. But for now, make sure they work. Okay, any other questions? Okay. This one, what did you use as a U?
the ln x.
Very nice. So U equals ln x. So the derivative of ln x is du. Derivative of ln is 1 over x dx. Okay, so I recognize 1 over x dx. Here it is, 1 over x dx. It's waiting for me here. I'm going to replace 1 over x dx by du. Integral. So 1 over, so ln x power 7. Well, u is ln x, so it's u power 7. Times what's left, it's 1 over x dx, which is just very easy integral. So it's the integral of u power -7 du. So I did this on purpose because somebody had a question what's a negative exponent. How would you do the power rule? So might as well. Okay, so u to the -7 is what?
U to the -6 over 6.
Very nice. U to the -6 over what? Over what you say?
-6.
-6 plus c. Okay, and then just equal to -1 over 6 times 1 u to the -6 means ln x to the -6 plus c. That's it. Okay, that's your answer. If you want, you don't have. If you don't want to have negative exponents, you could just do -1 over 6 ln x over 6 plus c. Also, that works. Okay, both of them are excellent.
Sir, why did we take the ln x as u and not the x ln x to the power of 7 as a u?
Try u equals x ln x to the power 7. All this to the of u, you'll see that it's, you have to try. Try, you're going to go in the wrong direction and it's getting too complicated.
But how can we figure which one to use as a u?
I gave you a hint. Okay, I give you a hint. You look for two things. One is when you have a function inside a function. So here I have ln x, a function to the power of something. So this is a hint that that's going to be my u. Okay, and another thing, another hint is that if I do the derivative of, let's say I choose u equals ln x, the derivative is 1 over x, oh, and 1 over x, I see it.
Okay.
Same here. Here I have x2 minus x inside to the power of a third. So that's my hint that that might be my u. And then the second thing I'm noticing is that x2 minus x, the derivative is 2x minus 1. Oh, it's here.
Okay, perfect.
So I recognize, so that's already a good idea that I chose correctly.
Okay, perfect.
Sure, does it have to equal to, so the derivative has to equal to 1 over x? Like, so those are the two things you're looking for? That it's in the function and that it's equal to the function around it? Or multiplied by it?
Yeah, off by a constant. Okay, if this was a 2x here, it would still, okay, off by a constant. If this was, instead of 2x minus 1, was 6x minus 3, so just 3 times more, it would still work.
Sir.
Yeah.
What happens to the x on the denominator of the initial function? Yes.
What happened to it? Well, I just replaced this by this.
Okay, thank you.
Yet 1 over x dx, 1 over x dx is du, so I'm writing du instead. Okay?
Yep.
So last example. Okay, so what do you put as u here?
Tan 3x.
Very nice. So u, this one's a bit more complicated. And so du is the derivative of tan 3x is secant squared 3x dx. Is that okay?
Isn't it
Yeah.
times 3?
Yeah.
What?
Isn't it times 3 because
Very good. Okay, so you're missing a 3 here, okay? Don't forget the 3 because there's a chain. When you do the derivative of tan 3x, it's secant 3x times 3. Okay, don't forget. So here on top I have secant squared 3x dx. So I'm going to isolate secant squared 3x dx. So I have to divide by 3. Okay, so that's the case where I divide. Because I want to make sure that what's left here, my differential secant squared 3x dx is exactly what I have on top. And then I think at this point it's pretty easy. So it's integral of, so 1 over e to the u times secant squared 3x dx, which is just du over 3. Okay, so I pull out a third integral of, well, this is just e to the negative u du.
Can we use the power rule?
No, it's not power rule. This is an exponential. So here you would have to do another substitution here. Okay, because we know that the antiderivative of e power x is e power x. But e power minus x, I mean, unless you want to do it just mentally, right? What should I derive to get e power minus u? Can you tell me?
minus e to the minus u.
Very good. Okay, so right away it's minus e to the minus u. Okay, so it's equal to 1/3 times minus e to the minus u plus c. Okay, if you derive this, you will get that.
Sorry, how does it become that? I don't understand.
How does it come from here to here?
Yeah.
So I know that the derivative of e power minus u, if you derive this, you'll get e power minus u times minus 1, and you'll cancel with this minus.
Oh, okay. Thank you.
So that's it. So it's minus 1/3 times e to the minus, well, u is tangent. That's the answer. Okay, and if, of course, if you don't want a negative exponent, it will be negative 1 over 3e tangent 3x plus. And that's your answer.
I have a question.
Yeah.
Another way to find the minus e to e minus u, like the from step 2 to step 3. Is there another way to find it?
From here to here?
Yeah.
Yeah. Let me show you here on the side. Okay, so let's say you were so 1/3 integral e negative u du. So I will do a substitution here. Let's call it, so I already used u, so I'm going to use v. So v is negative u. So dv is negative du. You with me?
Yeah.
Okay, and so du is equal to negative dv. Okay, then I replace. So 1/3 times the integral of, so e power negative u, so e power v, times du, which is negative dv. Get it?
Yeah, I understand.
And then I put the minus in front. So minus 1/3 integral of e to the v dv, and integral of e to the v dv is just e to the v, right? You integrate e to the x, is e to the x. So it's negative 1/3 e to the v plus c, and then v is negative u. Okay, that's what you have here. Same thing.
So I used this second method, but my u was 3x, and I got the same answer you got. Is that okay?
Excuse me, what did you do?
I used this second method where you do a double substitution, but my u was 3x.
Your u was 3x?
Yeah, and it gave me the same answer. My second value was v, and that was minus tan u.
So you put u equals 3x,
Yeah,
then v equals 10u?
yes, minus tan u, yeah.
Yeah, perfect.
Okay.
Yeah.